we have our final assignment due today, and we'll get graded assignments back for the end of the semester. I promise that. There's still some time. I'm happy to discuss with you your ideas beforehand, questions you might have about the project, and some places to look if you're not that familiar with the literature on these subjects. So let's chat about it before that, but it's due on the 11th. Okay? And then you have a month to write it down. Okay, so we've been talking about absorption and emission in light by atoms, a very important topic. And one of the things that's very important to understand is that much of our intuition about absorption emission can be gleaned by studying the classical problem of absorption of an electromagnetic field by a bound charge by an oscillating dipole. So although you probably learn about absorption emission in your standard quantum mechanics classes, thinking about time-dependent perturbation theory and Fermi's golden rule and all of that, in some sense it's missing some of the point, which is that you can think about absorption emission near a resonance of a bound system by thinking about a driven damped harmonic oscillator. Okay? And so if I have a charge bound on a string, in this case we think about it as just one electron bound to the core. Of course there's a resonance frequency and there's damping. In this case the damping is just due to radiation reaction. That's to say the damping is due to the fact that as the oscillator is driven, it radiates electromagnetic radiation, and that electromagnetic radiation carries away energy. So that's going to naturally damp the system, even if there's no other friction in the problem. And just from classical mechanics, the work done on the charges, which is therefore the power absorbed, or the rate at which work is done on the charges, which is the power absorbed by the charge, then time averaging off over the rapid oscillations of the driven of the oscillating force, that power is then related to the imaginary part of the polarizability. Okay? And we connect this to the quantum mechanical picture by looking at this two-level atom and calculating the induced dipole moment, which is coming from, in this case, the generalization of the Schrödinger equation, including damping, which we call the master equation. And the induced dipole moment then is related to the coherences that are driven, which are representing the superposition of excited and ground states. And we define that in terms of the components of the block vector. The off-diagonal element here was related to, in the standard jargon, rho GE has a real and imaginary part. The real part is called U, and the imaginary part is called V. And those U and V terms are related to the real and imaginary parts of the polarizability, because the real part of the polarizability tells me how much of the oscillation is in phase with the drive, and the imaginary part tells me how much is in quadrature. And so the absorbed power, according to this formula then, is related to this, actually in this notation, the negative of the V component. V, as we'll remind ourselves, is negative, so this is overall a positive number. And that power absorbed, we then can relate to the rate of absorption by just saying, well, every time I absorb a photon with energy h bar omega, so the rate at which energy is absorbed is the h bar omega times the rate at which transitions occur, the rate at which absorption happens. Okay? And we call that rate more generally the stimulated rate from the point of view of Fermi's golden rule. And when we plug this in, based on Fermi's golden rule, we got this expression where we use Fermi's golden rule with a density of states associated with the lifetime broadened excited state given by the Lorentzian. And this Fermi's golden rule, which is the time-dependence perturbation theory solution for the transition rate, is exactly the same thing that we get from this expression if we plug in for V based on the perturbative solution to the master equation. So this picture of absorption by Fermi's golden rule is exactly what we get from thinking about driving a dipole and then asking how much of energy, or what is the rate at which energy is absorbed by that oscillating dipole. And the regime in which this makes sense, which these are connected, is the regime number one, where the transients have died down. So this is not the regime of Rabi flopping. Rabi flopping is really a truly quantum mechanical probability amplitude kind of evolution. Whereas the driven damped oscillator is in a regime where dissipation has kicked in and steady state is being reached. Okay? So more quantitatively, what we discussed is if these were the optical block equations, also known as the master equation. And we looked at the steady state, right? This is my U plus IV in steady state. Then we plug this steady state coherence into this equation, and we arrived at a set of rate equations. And those rate equations then are this Fermi golden rule picture of transitions. And what we saw, if we then looked at in steady state, what the population is, in this case, we're talking about a two-level system in which population is conserved, and we plug that into this expression, then we found that in steady state, the population in the excited state was equal to the ratio here of gamma stim divided by 1 plus 2 plus, what am I doing here? Better write this out. So this tells me that the number in the excited state as a function of time is equal to so this tells me then that in steady state, the number in the excited state is equal to the stimulated rate divided by gamma plus twice the stimulated rate, which is equal to S over 2 divided by 1 plus S, where S given by this is equal to this expression, given this expression for the stimulated rate, and we call this the saturation parameter. So the saturation parameter is a very important parameter in thinking about absorption and emission of light by atoms, because it tells us, in some sense, how strongly we are driving the system. The amount of population, if I start in the ground state, the amount of population that I drive into the excited state depends on the saturation parameter. When the saturation parameter is small compared to 1, then the population in the excited state is approximately the saturation parameter over 2, which is much, much less than 1. And the population in the ground state then is approximately 1. I mean, it's 1 minus that small amount. So this was the perturbative regime, the regime in which I can think about my atom as a linear response. When the saturation parameter is small compared to 1, most of the population stays in the ground state. I create a little bit of coherence. I create a little bit of oscillation. And I can really, in that case, think about my two-level atom, or my atom in general with the near resonance, as a linear responder. That's to say, it has a linear response function where the polarizability is independent of the intensity. It's some number that depends on the oscillator strengths. On the other hand, when the saturation parameter becomes big compared to 1, then the population in the excited state goes to 1/2. And of course, then half of the population is taken out of the ground state. And in this case, we say that the transition is saturated for obvious reasons. So the last thing we discussed last time was how do we characterize the physical parameters under which the saturation parameter is big or small. It depends on this ratio. So it depends on the lobby frequency, which depends on the intensity of the field and the oscillator strength. It depends on the detuning, and it depends on the natural line width. And so there is, as we discussed last time, it's convenient to re-express this in the following way. So I can write the saturation parameter. Let me multiply everything by 4. So this becomes 2 omega squared over delta squared. Sorry, gamma squared, divided by 1 plus 4. The saturation parameter is equal to, well, it's proportional. This is the saturation parameter on residence. And this is, it falls off like a Lorentzian. For the detuning big compared to the line width, this falls off like 1 over the detuning squared. And the saturation parameter on resonance is 1 when the Rabi frequency is equal to the line width over root 2. But we often express that in terms of a characteristic intensity that is a characteristic of the atom. It tells us, if I am on resonance, how much intensity do I need to shine on the atom in order to saturate the transition? And we calculated that saturation intensity. And it's some expression here. And it's equal to h bar omega cubed over c squared times gamma over 12 pi. So it depends on the oscillator strength through gamma, and it depends on the frequency here. All right? Right. So saturation, let's look a little bit more carefully now at what happens in the context of saturating this transition. Let's look now at this expression for the steady state coherence more generally when I have saturation. Okay? So in steady state now we can look at this difference. Let's plug in what we got over here. So let's write a few more things down. So this was the steady state. This is rho EE in steady state. Rho GG in steady state is equal to 1 minus rho EE. That's equal to 1 minus S over 2 divided by 1 plus S. And so the population difference between the ground state and the excited state is equal to 1 over 1 plus S. This can't be right. This is going to be wrong here. This is plus. So we can plug that in over here. So the difference between the ground state and the excited state in steady state, 1 plus S. Plug that in over here. And we get U plus IV in steady state is equal to gamma over 2, 1 over 1 plus S, which is then equal to gamma's this over 2. Oops. Right. So, what do we see from this expression? Well, let's plug back in here for S. And that's then equal to right? So, if I put all of that together, what I see is this is equal to minus So, what do we learn from this expression? Well, when the saturation parameter was small, this term is gone. Right? Then we just had our Lorentzian. Let's sketch that out again. If I look at let's look at minus V as a function of detuning. So minus V is equal to gamma over 2 divided by this stuff. What do we see in that case? Well, depending on the value if omega is tiny compared to the line width, then we can neglect this term, in which case the line width of the transition is given by gamma. That's the natural line width. That's the full width at half maximum of this transition. However, when I start cranking up the saturation parameter, when omega is big compared to, well then this thing has its full width at half maximum broadened. I'll call it PB, where gamma PB is equal to the square root of gamma squared plus 2 omega squared. From the, if I were to write this, factor out in gamma squared over 4, you see that there is an increase in the line width. That increase is exactly equal to the square root of 1 plus I over I sat. And PB stands for power broadening. So, if I crank up the intensity enough that the intensity gets to be on the order or bigger than the characteristic intensity of the atom, the so-called saturation intensity, then I broaden the line width. Broaden the line, and that is what is known in laser physics as power broadening. All right. Let's leave this up here for a moment. We're going to use this later. There's one last idea that I want to emphasize here in the very basics of the interaction of two-level atoms with light and the absorption emission, and that's the notion of photon scattering. So, what we just erased over here, first of all, we had a notion of the absorbed power. We can, from our expression for the absorbed power, define an absorption cross-section, an effective area presented to my flux of energy that is being absorbed. So the intensity of the light is, of course, the energy per unit time, per unit area incident on the system. And I can then define the absorption cross-section such that this is the effective area presented to the light by the atom. So the atom is like a little bullseye with cross-sectional area. The cross-section sigma, the absorption cross-section times that is the power absorbed. So let's calculate what that absorption cross-section is. Well, we said that the absorbed power here was given by h bar omega L times the stimulated rate. Okay? And this is then equal to what? Well, this is equal to the stimulated rate, which we just erased, but let's write it down. This was for S, much less than 1. Okay, so what does that tell us? That tells us we can calculate this absorption cross-section now is equal to h bar omega L over the intensity. The saturation parameter was the intensity over the saturation intensity divided by 1 plus 4 delta squared gamma. That's our saturation parameter. And then we have gamma over 2. Yeah, I think that's right. So this then tells us this is equal to omega L over I sat over 4 gamma squared gamma over Well, this is not a particularly useful expression as it stands. Let me state a few things. First of all, let's look at this on resonance. Let's look at what this absorption cross-section is on resonance. On resonance, delta equals 0. The absorption cross-section is equal to that. And then we can plug in the expression we had. We calculated the saturation intensity in terms of the line width and all of that stuff. Plugging that in, and what do we get? What we get is 6 pi c squared over omega squared, which is equal to 6 pi times 2 pi over lambda, I'm sorry, lambda over 2 pi squared, which is 3 lambda squared over 2 pi. So one lesson we learned here, and this is a very important lesson, is that if I have a two-level atom with a unit oscillator strength, then the resonant absorption cross-section is basically lambda squared. It's not equal to the Bohr radius squared, which you might have guessed, which is tiny compared to lambda squared if we're talking about an optical transition. So the atom presents a very large cross-section for absorption. Yes?
So how come the same expression is used for multi-level atoms? Or what's the connection?
The issue here has to do with I've swept some details under the rug here, in that I assume that D dot E, that this expression is, which comes into all the interactions, that this was, if we really were to go into the details of this, all the details that all you guys have been studying for the last few weeks, there's all kinds of stuff that are related to Clebsch-Gordan coefficients and 6J symbols and all of the aspects of the oscillator strength associated with this two-level transition. When I write down this expression, this is the expression that is appropriate when I have what I call a unit oscillator strength. So that ignores all this stuff about the details, about the particular two-level transition that I'm drawing. In general, the cross-section is going to depend on the oscillator strength. This is the problem for a unit oscillator strength. If I have a multi-level transition, then I have to put in all the details of what is the Clebsch-Gordan coefficient associated with that particular transition, and each transition is going to have a different, slightly different cross-section depending on those Clebsch-Gordan coefficients.
And I guess also depending on the wavelength associated with each transition.
Well,
so this is assuming they all, yeah.
This depends on that. So this wavelength here is the wavelength associated with that resonance. Okay. Now, quite often you will see, in many books, you will see it written like this, without the factor of 3. Now, what the heck is that about? Well, again, what I'm assuming here is a fixed polarization. of the light. If I'm looking at absorption by sunlight, only 1/3 of the intensity is in the particular polarization that drives this transition. And so often you will see it without the factor of 3, and that's a factor associated with unpolarized light or an unpolarized atom. If I had a mixture of all the magnetic sublevels, then it's going to absorb equally all the polarizations, and only 1/3 absorbs any one polarization. So in an unpolarized circumstance, you'll often see this written. But if I have a definite transition with a definite polarization, and I take the oscillator strength to be 1, this is
It's about this at 1, you just have a different constant.
That's right. That's right. I mean, if it's not, I mean, if I'm talking, you know, if I had a multi-level atom, and this Lec23 coefficient is 1, but this coefficient is the square of this Lec23 coefficient is 1/3, then the cross-section is just 1/3 as big. All right. But what I was really, well, okay, before I get to that, I guess I should say one last thing. And then I haven't said anything yet about this question of photon scattering. What I'm talking about right now is absorption. But I wanted to mention one other thing in this context, which is that another way, a way that we often write the saturation intensity, is solving, instead of writing out that complicated expression, we can see right here, if I solve this equation for the saturation intensity, then the saturation intensity on resonance is equal to the resonant, let me call this 0 to emphasize that this is on resonance. This is the familiar expression to me for the saturation intensity. Not that other one with the 6 pi's and all that, I don't know what the hell that is. But I know what this is, because this is energy per unit area times the rate, which is an intensity. So this is my absorption cross-section, I plug this in, this gives me the saturation intensity. Notice that the cross-section off resonance is equal to the resonant cross-section, and then it falls off like Lorentzian. Okay? Of course, this was in the perturbative regime. In practice, I really should have, in addition to this, the saturation. So in principle, this is really the power broad line that was there if we were to crank up the saturation parameter. All right. However, what I really wanted to talk about here was not necessarily the absorption cross-section, but the idea of photon scattering. So, in a two-level atom, or in an atom, no electromagnetic energy, or I should say this way, in an atom, if a photon is absorbed, it is ultimately emitted. That is different than, say, in matter with many more degrees of freedom. If I have a molecule, I can turn absorption to an electronic state into mechanical rotation or vibration of the nuclei. But here, the electronic energy, if I excite it, eventually it's going to come back down to the ground state. It might be metastable, it might stay around in some long-lived level, but eventually it's going to come back to the ground state. And it's going to come back as a photon. So when we talk about the power absorbed, if I think about this atom, light comes in, but light goes out. So any power that is absorbed and doesn't go back into the beam that went in must be scattered radiation. Where else is it going? Nowhere. So for an atom, the absorption is equivalent to scattering. So I can equivalently think about this absorbed power as scattered power. And from this, I get the so-called photon scattering rate. So the photon scattering rate is, which I'll call little gamma sub s, is the scattered power per h bar omega. That's the rate at which photons are scattered. The scattered power is h bar omega times the rate of scattering. And that is given by, in this case, s over 2 gamma for s much, much less than 1. Or more generally, it's s over 2, 1 plus s times gamma for arbitrary. Yes. How do we see this a little bit more clearly in the optical block equations or the rate equations? So recall, we had from the optical block equations or the master equation, the rate of change of population in the excited state was given by minus gamma, this population. And then we had over here minus we had this expression. Let's look at this a little bit more closely. This is minus gamma g times minus this, the imaginary part of rho g, which we call equal to v. Remember, v was the imaginary part of that coherence. So let me write this as plus this times minus v, because minus v is a positive number. What does this say? Well, remember what we just had. We had this at the very beginning of the lecture. What is this? Remember, v was related to the amount of power that was absorbed, right? That power absorbed was equal to this expression times h bar omega. So power absorbed over h bar omega is equal to this. This is equal to the rate of absorption. So the rate at which I'm absorbing, well, that in steady state is equal to the rate at which I'm emitting. However, let's be a little bit careful about this. Because remember, there's two kinds of emission. We had one emission we called stimulated emission, And one kind of emission we call spontaneous emission. Remember, this expression in steady state was equal to gamma stim times rho GG minus rho EE. So, the amount that's absorbed in the problem in steady state is equal to the amount that's emitted. So in steady state, the rate of absorption is equal to the rate of scattering. Really, I should talk about this emitting. This is scattered light. Instead of emitting, this would go to the scattered light. Because there's also stimulated emitted, but the stimulated emission is emission that goes back into the beam from which it came, and therefore does not count as absorbed power. The absorbed power is the stuff that's being taken out of the beam, and all of the stuff that's being taken out of the beam is scattered. So our rate of absorption in steady state, the rate of absorption is equal to the rate of scattering, which is equal to gamma rho steady state. Here's the picture. We have the ground state, we have the excited state. We're driving the system. If we just had stimulated emission, everything would go from the beam back into the beam. But some of the light goes elsewhere. The amount that goes elsewhere is equal to the rate at which spontaneous emission happens. The rate at which spontaneous emission happens is the 1 over the lifetime times the fraction of the population that's up there. And thus, the scattering rate is equal to the spontaneous emission rate times the fraction of the population in the excited state. And the fraction of the population that's in the excited state is S over 2, 1 plus S. Does that make sense? The key idea here is that the only light that's taken out of the beam is scattered. So any light that is being attenuated, attenuation of the light as it passes through the atomic vapor is not due to exciting phonons in the system or other kinds of heat. It's due, in this case, solely to being scattered out of the beam. And that rate of scattering is due to the spontaneous emission, and that spontaneous emission happens at this rate depending on the fraction that's in the excited state. Okay? So these are all extremely important concepts in understanding how we manipulate atoms, especially with lasers, as they absorb and emit light. All right. So we have all the fundamentals in hand now, and we want to now turn our attention, starting today and through the rest of the semester, on the problem of cooling and trapping of atoms through their interactions with electromagnetic fields. Now, what we've discussed to date in the last number of weeks, we've discussed the interaction of atoms with light, we've talked about this in terms of absorption and emission of energy. So we've thought about this in terms of there's some ground state, there's some excited state, and all the stuff that we just drew. And this had to do with the internal degrees of freedom that is to say, the binding of electron to the core. But if we want to talk about cooling, what I'm talking about here is cooling and trapping. This is related to the center of mass. That is to say, we want to consider the situation in which we can take a room temperature vapor of atoms and slow down its motion to close to absolute zero, and then trap those atoms in very shallow traps. So we're not, we want to generalize our discussion beyond thinking about the internal degrees of freedom. We also want to think about what we call the external degrees of freedom. That is to say, the center of mass motion. Of the whole atom. So, in order to do that, we want to think not just about energy, we want to think about absorption and emission of momentum acting on the center of mass of the atom. Now, we can get a lot of mileage out of that, understanding that, in the same way that we discussed in the last few lectures, our intuition about the absorption emission of energy by thinking about our atom as a classical bound harmonic oscillator. We can get a lot of mileage out of that by thinking about the absorption emission of momentum that way as well. So I want to begin the discussion by thinking about just a classical description of this problem, and then we will generalize this to the quantum problem to understand some of the differences. So, recall electromagnetic fields carry energy and momentum. This goes back to Maxwell, of course. We have the Maxwell stress tensor, everyone's favorite. And from that, you recall, we have, of course, the Poynting vector. Poynting was a person, even though it points. Which is the energy flux. That is to say, this is the energy per unit time, per unit area that's flowing in my electromagnetic field. The time average of this, the magnitude is the intensity. We also have momentum flux. the momentum flux is S over C. And if I were to take this momentum flux and integrate it over a surface, this would equal to the momentum flux through the surface. And if all of that momentum flux were absorbed, well, what is momentum flux? Momentum flux is momentum per unit time per unit area. If I integrate that through the surface, that's the rate at which electromagnetic radiation is passing through that surface. And the rate of momentum is force. So my momentum flux is another word for radiation pressure. That is to say, electromagnetic radiation, if it's propagating, can be absorbed, can exert a force on matter. And the amount of force is related to how much of this momentum flux is absorbed. So radiation pressure is a classical notion. And we can get a sense of how big the radiation pressure is thinking about this acting, an electromagnetic wave acting on a dipole oscillator. So let's think about then the mechanical force of an electromagnetic wave on a dipole oscillator. So let's imagine we have a bound charge. Let's say it's got some negative charge, got some positive charge, bound together with some harmonic oscillator binding them together. And I'm going to drive this with a plane wave. Well, not quite a plane wave. Let's allow it to be a finite beam that has some finite extent, so that the amplitude is not constant. It's a finite beam. So my electric field, as a function of position and time, is the real part of some amplitude, which has some slow position dependence, and then I have the phase of the wave as it propagates. Okay, and then the magnetic field is the perpendicular thing. E cross B is K. So let's think about, just classically, what is the force exerted by this wave on this set of bound charges? Well, the force is this, I got the Lorentz force. There's each charge exerts, there's an electric field, there's a magnetic field, and then we're going to look at this time averaged over a period of this rapid oscillation, just like before. Why is there a magnetic force? Well, the electric field is going to drive the dipole and create a moving charge. It's going to create a current. And so if I look then at the magnetic field, it will exert a force on that current. And with the direction of that force depends on the current in front of me. So we expect that there will be a force in the direction of k. V cross B is in the direction of propagation. Let's look at this in more detail. So again, if I assume my bound charges are bound in a region that is small compared to the variation in the fields as a function of position, we can do a multipole expansion. So for charges localized in a region small compared to the wavelength of the laser or the light, then we can do a multipole expansion. And since we're talking about a neutral atom here, I hope we'll get to talk about ions before the semester ends. But for the neutral atoms, there's no monopole moment, so the QE summed over the charges, the lowest order, is equal to this force is the force on a dipole. And the force on a dipole is d dotted into the gradient of the electric field at the position of the center of mass. That is the force on a dipole, right? From classical electromagnetism. So I'm taking R here to be the center of mass position, which is essentially the nucleus. What about the other term? QV over C cross D. Well, the only thing that's moving here is the electron. Basically, we'll keep the nucleus is so darn heavy, it's not moving. So this is the position of the electron. It's motion. And the magnetic field here is equal to, it's in these units, the magnitude of E and B are the same. The direction of B is just different according to the wave vector. So there's the direction of the wave vector crossed into the electric field. That's the magnetic field. Right? K cross E is B. And if you like the other units, E over C is B, and then you don't have that C over there. So this then is equal to Q V dot E over C in the K direction. Using the famous back minus cab rule. Everyone knows back minus cab, right? And the velocity is in the direction of E and is perpendicular to K, so this is 0. And so this is the position of the electron. So this is Q R dot over C dot E, which is equal to E dot. Okay. So, what have we learned here? Well, let's put it together. The force force on the driven dipole has two pieces to it. We have the time averaged d as a function of time dotted into the gradient of the electric field as a function of position. Plus the time average of d dot dotted into the electric field as the function of position over c. How do we interpret these two terms? Well, let's look at them. They're two very different kinds of forces. They have different physical origins. I mean, they all have fundamentally the same origin. They have to do with the fact that we're driving dipoles and currents, and those dipoles and currents then interact with the E and B fields. But ultimately, they have very different effects on the motion and the force that's induced on this dipole. Of course, what we have here, let's assume we have a linear response. Our dipole, as a function of time, assuming that my field is weak enough that my harmonic oscillator just obeys Hooke's law, then the induced dipole moment depends on the polarizability. So let's all put everything back together. So let's take a look at this expression here. We're looking at the time average of d dot E. Remember, this is equal to the real part of this cosine k dot r minus, let me write it the other way, omega r minus plus the imaginary part sine minus theta. So let's look at now each of these terms and what they imply once I do this time average. The gradient doesn't change the time derivative, so the gradient of this is going to oscillate like cosine omega t times whatever the width is phase. And when I then do the time average of this, so let's consider each term. If I look at the time average of d dotted the gradient of E, plugging in what I have there, I see that this is equal to 1/2 the real part of the polarizability, E dotted into the gradient acting on E at the position. So, what is this expression? Well, this expression is is the gradient of 1/4 the real part of the polarizability times E dot E, or the magnitude of E squared. So this term in the force is a conservative force. It is the gradient of a potential. We know that because electric fields are conservative fields, right? They are derived from the gradient of a potential.
Well,
So
but
the
in
term...
this case, it's a electromagnetic field, and it doesn't have to be conservative.
What do you mean it doesn't have to be conservative?
Well, electric field can be caused by magnetic fields.
Yes.
And then you've got an electric field going in the current.
Sure, indeed, and that's I mean, those terms come in over here, right? Because that was the term that related to the force here. The force, I mean, it's really what I should say is the force due to an electric field alone is a conservative force, but the force due to a magnetic field is not a conservative force. Now, of course, the electromagnetic fields propagate and generate into one another, but the force due to an electric field alone is a conservative force. And we see that clearly here, because this force is the gradient of a potential. This is minus the gradient of what we call the light shift potential. So the light shift potential is equal to minus a quarter, the real part of the polarizability, times the square of the field, which is proportional to the intensity at the position. So this force has many names. It's sometimes known as the gradient force, or the dipole force, or the reactive force. Why? Well, it's got a gradient in it, so that's called a gradient force. It depends on this sort of the picture of, I have an induced dipole. That induced dipole then interacts with the field. And there is an energy of the interaction of that induced dipole with the field. And together, the gradient of that energy, if that interaction depends, if that amplitude varies as a function of position, and therefore if the intensity varies as a function of position, there will be a potential. And the gradient of that potential determines the force. It's called reactive because it depends on the real part of the polarizability. And the real part of the polarizability is sometimes known as the reactive component. So you'll see all of these terms discussed. What about the other term? Let's write that down. Well, this is what we just had at the beginning of the class. The beginning of the class, we said that the power absorbed was the rate at which work was done on the dipole. And that was equal to, in time average, this. So, the force related to, if I look at this term, it's equal to the power absorbed divided by C. And the power absorbed is equal to the integral of the Poynting vector that's absorbed over whatever, well, I should write it this way. The power absorbed is the intensity absorbed times, or the intensity that's incident times the absorption cross-section. That's the power absorbed. But the intensity over C was what we call the momentum flux, right? We had somewhere here, we had the Poynting vector over C, was a momentum flux. So this is just radiation pressure. Radiation pressure is related to the absorbed light. It's related, it's also known, this is also known as the dissipative force because it depended on the damping, right? If I write this out, you remember that the power absorbed, remember there's a dot here. So my cosine becomes a sine, and my sine becomes a cosine. So this is related to 1/2 the imaginary part of the polarizability of this over C. The reactive force depended on the real part of the polarizability. The dissipative force depends on the imaginary part of the polarizability. And it is what we call radiation pressure. There's yet one other way that this is called, and the most typical way you'll hear this called, this is what's called the scattering force. Why? Because as we discussed, in the context of the atom, no light is truly absorbed and goes away, it's scattered. So the force that is being exerted here is due to the scattering of electromagnetic radiation. In fact, this radiation pressure then, because we have this before, this radiation pressure is given by the power absorbed, which is equal to the power scattered in steady state, once the transients die down. And that scattered power, we said, was the rate at which photons are scattered times h bar omega divided by c. Of course, it's in the direction, we forgot when I did my the force here, there's a missing direction here because there was the E sub k. Remember that in my back minus cab rule? So I really should have that here. And omega over c is k. So, to conclude, what we see here is that the dissipative force can be understood as the scattering of photons with momentum h bar k at a rate depending on the rate at which photons are scattered. And so we have already our quantum mechanical expression for the scattering force, because we know from the optical Bloch equations what the scattering rate is. So we'll be able to pick that up next time. But what we see here importantly is these two very different kinds of forces. The scattering force having to do with the scattering and spontaneous emission of photons, and the dipole force having to do with the conservative potential, and in some sense, the stimulated redistribution of momentum between different wave vectors in a spatially varying field. Okay? To be continued.